As usual, if you can, please turn on your camera so we can have a little bit of better experience talking to each other. Okay, let's start. Again, I think Wayround joined recently, so if you can turn on your camera, Wayround, that would be great. Otherwise, let's start. The topic today is memory optimizations. Even though that's a compiler class, memory optimizations are very hard to do without some background on the hardware end. So today, we will start with some background on caches and memory. I will be relatively high level, but hopefully it'll give you enough details to appreciate what the compiler has to do afterwards. So I apologize for people who already took like computer architecture classes, which is typically not offered at UTSC. But if you did, you probably know a lot of this content, but hopefully, you still can refresh it in your head. And for others, that can be quite new content. Okay, so let's start. So this is just a quick summary on what we covered in the previous lecture. Remember, we talk a lot about pointers. You probably realize pointers are hard to understand at compile time. It's hard to do for humans. It's obviously hard to do for compilers. So accurate analyses are large and complex. That's hopefully the key, the takeaway you realize from several algorithms I showed you. There are many different options on how you can represent things and how accurate your analysis can be. So representation can vary. You can differently model heap, aggregate data structures like linked list or arrays. Your algorithm can be flow sensitive, it can be context sensitive. All of that changes the precision, but also adds extra complexity. We look at several different algorithms, address taken, Stingers, Anderson in a decent amount of detail. I just mentioned very briefly BDD-based analysis, and I go into decent amount of details on probabilistic example of analysis. So at least you get a feeling that things might be not 100% accurate, but probabilistic based on runtime analysis. There was one question on Piazza about address taking that I answered. Hopefully there's no any follow-up and people don't have any confusions, because it's a very simple analysis still used for some large graphs in industry compilers. Where the other algorithms are just too complicated. There's a lot of different trade-offs: space, time, accuracy, and safety, the key four metrics, but there might be others as well. And we show how one is can be traded for the other one, essentially. You have to choose the one that works the best for you. Okay. So this is just a repetition from the last lecture. So you remember what we covered last time, especially since we had quite a few people there. Now, let's talk about caches. So why the caches matters? Well, because when we think about memory optimizations, caches play a huge role there, right? Because they're part of the memory hierarchy. I'm pretty sure most of you have heard about caches, but how and how many details you understand their necessity and how they work. I'm not sure. So please ask questions if I go too fast or if I'm too slow, okay? So what are the things we want to cover about caches today? So first, how do they work? That's obviously an important thing. I'm obviously going to cover why we care about them and why caches are so important. So even though they're not part of the von Neumann architecture, so if you remember the von Neumann architecture basics, right, there is a memory there, but there's no caches. Caches are not required for the operations in terms of correctness, but without them, the performance, difference are humongous, right? So it's hard to imagine any modern architecture without caches at all, although that still happens in some niche areas. We're going to talk about what are the typical configuration that exists today. I show you some, relatively recent chips and how important are the caches there. You're going to see from the, the layout of the chip. And we're going to talk about some important cache parameters that will affect performance. Okay, so first of all, as I mentioned before, from the programmer's view, there is no cache. There is store, there is a load. Store goes to memory. To store the value, loads as an API, reads from memory, reads the value into a register from the memory. So this is something you probably covered in the B58, right? This is the classical API between the programmer and the hardware with respect to memory. So where is the memory in the modern chips and how important it is? As you can realize, there's so much research going on and people care. It does matter, but why so? So let's look at the typical Intel chip here. This is not the most recent, but still quite representative. So as you can see here, there are compute units, are those cores, right? Core 0, core 1, core 2, core 3. This is a 4-core chip, right? But is that everything? And how much area it occupies compared to other things? Well, as you can see, there are a lot of other stuff. So there is L2 cache, right? So this is something we're going to learn about, a level 2 cache. And you can see it looks different and it takes substantial amount of area here, right? And this is a private cache dedicated to each of the core. You see this is L2. That means there's not all, this is kind of external cache. There's also small cache inside of this core that is high to highlight because it's small and it's hidden, but it's still there. So it's not just the whole cache. And then there is this big part thing called shared L3 cache, right? So this is even larger space where a lot of, this is something you typically think about the cache when you look at the specs of your CPU. This is like something like 8 megabyte or 16 megabyte L3 cache, right? So this is last level cache. In this case, it's 3-level cache hierarchy. So as you can see, those caches occupy a very decent amount of area on the chip already. So if you ever wonder why I only had 16 megabyte of L3, well, because doubling it wouldn't find a space on the chip, right? It's going to be quite expensive. Obviously, there is also the memory itself that's important. So here you're going to see this PIS for DRAM interface, right? And this is DRAM bank that is actually off chip. Those are the pins that it's connected with the core, with their, SoC here. And this is the DIMM, right? So you see memory is outside. Memory can be integrated on the chip itself, but it has some severe downsides. So in a typical system, the DIMMs are separate. This is one of the, Samsung DIMMs. Any questions about that? So this is how the memory looks like at a very high level.
So where is L1 cache then?
L1 cache is in the core itself. It's not trivial. It's relatively small. So the typical L1 caches, first of all, there are 2 L1 caches, right? So this L2 and L3, they are so-called merged data and instruction cache. Remember, there are 2 different caches for data and for instructions, right? I'm not going to talk too much about this course. That was something covered in computer architecture classes, but there are 2 different caches. In L1, those caches are tiny and they're very tightly integrated with the core because they need super low latency. So to give you a feeling, L1 cache has a latency of 2 to 4 cycles. 4 is the worst case. So 2 cycles, it's like a latency of an addition, right? So it operates almost at the speed of instructions, right? And because of that low latency, it's not a nice standalone structure that has long wires, right? That would make long latency. So it's somewhere in this core. There's one thing for data and one for instruction. They're not too large, so it's not a big deal, but it's somewhere here, right, in this core as well. One for data. There's also TLB somewhere here as well. We're not covering all the different cache structures, but so essentially it's not an easy thing to identify. Let's put it this way. So Intel knows, but I don't. Right. But it is there, and it's typical sizes are like 32 kilobytes, 64 kilobyte, right? Right. So in terms of space, it's not dramatic. So to give you a perspective, so L1 is usually, obviously private here, and it's like 64 kilobyte latency as like 3-4 cycles maximum. And the same for instructions. L2 in this case is the second layer, so it's still private, but its capacity can be something like 512 kilobytes, right? It exists here because putting all this thing in here would make the latency much higher, right? But there are cases where I want to still have dedicated larger cache, so the core won't interfere. Remember, if I had this shared cache, this is shared across 4 cores. The cores might compete for cache, right? Because it's all shared. And that has negative effect on performance. So there is a reason why this second layer exists here. It means there is not enough area and low latency to build this cache. Again, I'm not going to cover in this course, but essentially there is a trade-off. The larger the cache, the higher the latency, right? There's no like miracle there. So this thing is going to be on the order of, I don't know, 8-10 cycles. And this thing can be 20, 30, if not 40 cycles, right? So larger means slower, right? There's no miracle there. And so sometimes you need a small but fast, and that's a trade-off we do, right? Okay. There's also DRAM memory, and there are a lot of other parts here, peripherals of different kinds, but it gives you a sense that memory is area-wise, takes at least as much space as compute itself, right? And it was not always like that. It's over the years people realized the importance of memory. Okay. Did I answer your question?
Yes, thank you very much.
Yeah. Okay. So why why do we need to have cache? So if we would have an ideal memory, such as zero access latency, infinite capacity, zero cost, and infinite bandwidth, there would be fundamentally no need for caches, right? But that ideal memory doesn't exist. So the problem is why that doesn't happen, and even approximately doesn't happen, is because those requirements oppose each other. Bigger in terms of capacity means slower, right? Again, I'm not going to cover the design of caches in this course, but if you think about it just fundamentally, the larger I build the cache, somehow I need to keep the metadata, what is stored where, right? The more metadata I have, the harder it is to search these elements in parallel, right? So I either need a lot of circuits to search in parallel, or I would need to make things sequential so the latency adds up. So if even if the pins are not a problem, the problem would be in these metadata structures that makes it slower. So the larger the cache, the slower it is. Faster is also more expensive, right? As you can realize, there are different memory technology. I'm going to cover a few in this lecture, again, very briefly, like SRAM and DRAM, and there's SSD, there's non-volatile memory, there's disk, obviously. And always the fastest is the most expensive, because to be very efficient in terms of speed, I need to use a larger granularity or more complicated designs, right? And that's costly, right? So if you do the math on SRAM versus DRAM, you would realize that actually they have several orders of magnitude in cost per bit, right? And people propose actually a lot of different designs for memory. only very few stick because they find a nice niche areas. So SRAM to appear first, then DRAM appeared like 30, 40 years ago. Then SSD find a nice niche place between the disk, right, that exists for for a long time, and the memory, and finally non-volatile memory, like Optane from Intel starts gradually to get some traction and try to find space between DRAM and SSD. And the reason for that is because our applications are so memory hungry, so we need higher capacities, but ideally with the latencies that are low. Higher bandwidth is also extremely expensive. Again, in my computer architecture class, I'm going into a lot of details on what in the design make high bandwidth is so difficult to get. But just trust me on here. Like if you want to get very high bandwidth memories, it's quite expensive. So one of the reasons why I say hardware for GPUs is so expensive, right? Modern GPUs is because they had to use a very fast memory. Sorry, not just fast, but high bandwidth. So for example, if you buy more than 2080 Ti GPU, right, it's going to use a special DRAM, not the one you use in CPU, called GDR6X. And that memory, I don't know, bandwidth-wise, it can be 8x, 10x more bandwidth. Latency is more or less the same, maybe even slightly worse, but the bandwidth is so much higher, right? Why it's needed? Because graphics applications needs it, like because you want to process a lot of things in parallel. Machine learning applications also need it. All of them are very, bandwidth hungry. Okay, so as you can see, all these dimensions are conflicting to each other. So bigger takes longer to determine the location. Here there's examples of memory mentioned: SRAM versus DRAM versus flash versus disk versus tape, right? So there are all these dimensions. There are a lot of different new fancy technologies people explore. For example, there is like tape exists for I don't know how many years, 50, 60 years, like it was always there, but it's extremely slow. It's more like archival storage. Even there is some innovation in the last maybe 5, 6 years. I think people at Microsoft and University of Washington look at using actually DNA to store the information. And it has a better density, much better density than tape. And it doesn't need, it doesn't die out. It doesn't need any recovery thing. So the tape starts to die out over time. Like after 50 years, you get some issues with it. So there are alternatives in all these layers. So people always try to innovate. So high bandwidth is hard because you need more banks, more ports, higher frequency, or faster technology, or a combination of all of that. So it's not for free. Okay, so again, I understand a lot of you are not from, doesn't have a lot of engineering background, but I give you a little bit of background on DRAM and SRAM so you can at least understand how they're physically different. Again, depending on whom you take B58 from, that might have been covered there or might not. In my version, I actually covering that, but in some others, it might not be covered. So I'll try to cover it here. So DRAM stands for dynamic random access memory. Why is it random access memory? Because in the early memories, there was like some limitations on how you can read. It might be like sequential memory that you read. Here it's really random. It means that reading certain pieces of that memory is almost the same latency, or pretty much the same latency as anywhere else, right? So it's random access is fast. Important part of DRAM that you need to understand, without knowing too much about it, that it has capacitor. So it has capacitor that the charge of which indicates the stored value. The easiest way to think about it is your 0, 1 is essentially high charge versus low charge, right? That's the easiest way to think about it, right? It might be a little bit more complicated than that, but you can think for simplicity, just 0, 1 means high charge versus low charge. And for that to happen, you need to have one capacitor and one access transistor. And that's the Rother design that needs to that. And there's a bit line and the row enable that allows you to read an individual bit. So the key thing, without going deeper into DRAM organization, the very important part for you is to understand is that, and that's a big weakness of DRAM, is that capacitor leaks charge over time. So it means if I leave my memory without recharging it, with the power all the time, it's going to lose the charge. And essentially, if you actually, there is like all these famous movies about people trying to steal information from, from someone. And there were rumors that if you actually grab DRAM and freeze it, right, in a special way quickly, you might actually store the information. And it's not completely impossible. In fact, if you actually, like I did some experiments in grad school, so if you actually reduce the default parameters of refreshing the memory, recharging it, it can actually retain most of the values for as long as a few seconds, right? So it's not complete science fiction, right? That's what I'm trying to say. But usually to have a reliable operation, the refresh rate is around 64 milliseconds, right? This is how frequently your DRAM is refreshed, right? As you can imagine, if you don't refresh, some values will lose charge and will go to ones become zeros, right? And essentially everything is indistinguishable. But due to manufacturing process, the cells had very different strengths. So some might lose charge in 10 seconds and some might lose charge in 100 milliseconds, right? That requires you to have some standard that manufacturers build that defines how quickly you lose charge. But the important things for you to remember, DRAM is, compared to SRAM that I'm going to define next, is relatively slow. It's cheap because it only had one capacitor and one access transistor, but it leaks charge over time. That's its key characteristic. Like every time you reboot the machine, the memory content is gone, right? You need to read it again, right? So that's an oscillation state. And you can see it quite how slow the process is. I think until SSD starts to become a mainstream as used in all the laptops. I actually laptops, all the laptops with hard drives. Like I'm old enough to remember those ones. So those ones actually were very slow to boot, right? Because they were reading everything from a magnetic disk. And also, if you're unlucky and didn't, they didn't go to sleep mode, and you had that hard disk spinning while you're running with your laptop, right, on your backpack, it might actually, crack it, right? So you can actually lose information. Anyway, another important type of memory is SRAM. And this is technology important because that's the one that's used for everything that is the fastest, right? So it's called static random access memory. And it has two cross-couple inverters that are used to store a single bit. Its feedback path enables the stored value to persist in the cell, right? It had 4 transistors for storage and 2 transistors for access. So it definitely had a more expensive design, right? So the SRAM is way more costly to manufacture, but it has lower latency because of its design, okay? And that lower latency make it an attractive technology to be used for both registers that needs to be super fast, as you know, and caches. But just remember that very frequently people associate the layers of the memory hierarchy that I'm also going to define in this lecture with this technology. And that's not always correct. Layers of caches are based like L1, L2, L3 cache, and so on. It's not based on the technology. It's based on the logical fundamental organization. You might have a system, in fact, they exist, with like L4 or even L5, like IBM built systems with so many layers of memory hierarchy. And L4 there might not be based on SRAM. It might be actually based on some fancy DRAM new standard, right? But it operates as a cache rather than the memory. And so its behavior can be different. So you can think of one layer, like if you really need a lot of, a really large cache, you can actually use DRAM for that in some cases, okay? So like sometimes people use interchangeably saying SRAM storage meaning cache. Remember, this is not always accurate, okay? Okay, so why do we have memory hierarchy, right? Because we want both fast and large. We want a lot of memory because our applications right now are very memory hungry, and we cannot achieve both of that with a single level of memory. So that's fundamentally what the technology limits us. So the idea that exists for a lot of years, and it's one of the breakthrough ideas in computer architecture design, because it's very, we get used to this idea now, but it was not always the case that people think about the system this way. The idea is to have multiple levels of storage, progressively bigger and slower as the levels are further away from the processor. And we ensure that most of the data we usually keep in the faster levels, so that we create an illusion that we had a faster storage with large capacity. Okay, so that sounds easy. In practice, it's not that always easy to achieve it, but that's the goal. So essentially, the best way to think about it, there is trade-offs here. There is fast and small, right? And big but slow. So this is something where we want to back out things. It's cheaper per byte. This is faster per byte. If we had a good locality, the reuse in our applications of the data that is frequently used is most of the time is serviced from the fast storage, then we can essentially create an illusion that we had a lot of memory and we would bring things from here to a faster memory, right? So essentially, instead of having this one monolithic thing, I have a few smaller elements. So you can think about this as L1, this is L2, and this is memory, right? And those intermediate layers allow me to create that illusion that most things resides in this memory instead of here. Well, this one gives me capacity. Any questions so far? Is the basic idea clear? Okay. So the fundamental trade-off, as I said, fast memory but small, large memory but slow. And the idea, as I said, is memory hierarchy. So we had CPU with a register file, we had a cache here, and there are multiple layers potentially. There's like long distance here until main memory. Remember, I show you the design of a real chip, right? The memory there was away from the CPU, right? It was actually going off chip, right? So the memory was not on chip. This is why we usually draw this line as long lines, because these things is going to be hundreds of cycles, right? There are a lot of dimensions here to deal with: latency, cost, size, and bandwidth. Okay. Again, I'm not going to go into all these details there. You just trust me that there is a significant difference, that the economics of the process makes sense. We now talk about the basic stuff behind caching that compilers will exploit. And the first thing is so-called temporal locality. So what is the temporal locality? So the idea here is to store recently accessed data in automatically managed fast memory called the cache. And the anticipation is that the data will be accessed again soon. So this is why it's called temporal. So the observation is that we write the code where the data is not randomly accessed across all memory. If that would be the case, caching idea would never work. But there is an idea is that when we write our algorithm, there is the same piece of data that we routinely access again and again. So this is the metadata, depending on the algorithm, it can be different things. But it apparently the code is written in a way where that is frequently the case. And that is called temporal locality. So temporal locality principle simply says that the recently accessed data will be again accessed in the near future. If you say this is a fundamental rule, it's not as fundamental like, as traditional laws of physics. It's more like of an observational principle that the code we write tend to have this behavior. And this is essentially where the inventor of the cache, John Wilkes, said about the memories. They didn't have the name cache back then. They were called slave memories. Back then, there was just the memory and the tape, right? And essentially what he says is, it's not actually far fundamental from what we're saying right now. His observation is that the users discuss of a fast core memory of, say, 32K words as a slave to a slower core memory of, say, 1 million words, in such a way that in practical cases, the effective access time is nearer that of the fast memory than that of the slow memory. So essentially, we never can get exactly the same latencies on the fast memory, but if on average we can almost always see it and get access from the fast memory, that we can create an illusion of a large, slow memory in terms of capacity, but with the access latency of a fast memory. So this was the first principle, temporal principle. But the cool thing about caches, they not only benefit from temporal principle, but also from the spatial locality principle. The idea is to store addresses adjacent to the recently accessed one in automatically managed fast memory. So we logically divide memory into equal size blocks. This is something you probably have heard as being a cache block size, right? If you've heard about caches and heard at least a little bit about it, the typical block size these days for caches is 64 byte, right? And I'll explain you how that happened. And then we try to fetch the access block in its entirety. And then anticipation is nearby data will be accessed soon. Again, why this happens? Again, this is because the way we write our code. Very typically, if I read from an array, even if I had some patterns across the cache, I tend to access nearby values in the array very frequently. So if you're ready to bring a 4 byte from that array, it might be better to bring a lot of, or at least some nearby values as well, right? How much and why is it exactly what it is? We can, if I have time, I can answer those questions. But essentially, we always bring more data than we need. So if you write a load that requests 4 byte from memory, you're going to get 64 byte. And all of this 64 byte will be stored in anticipation that you would need the nearby data soon, right? And if you think about it, you realize that actually very common behavior of your program. And the principle here is that the nearby data and memory will be accessed in the near future. This is, for example, instruction behave this way. Like when you look at the instruction stream, when you execute your binary, you execute them one by one, right? Occasionally you have to jump due to branches, but most of the time you just sequentially execute, right? So it means that if I read an instruction, I probably want the nearby instructions because I'm going to need them soon anyway. So there's no point to bring one instruction. I better just bring 6 or 7. And that's what IBM implement, right? A so-called instruction cache, right? And this is the design. So it's interesting that the first cache, when the first caches people tried to build, they were actually looking at 2 different principles. One was looking at temporal locality, one was looking at spatial locality. It turns out we can have one thing benefiting from the 2 things, right? But the first motivation was this way. Any questions? Okay. There are no questions. Let's move on. So how we can make cache performance higher? Well, what we can do as a compiler. So essentially for us, all this tutorial was so far about what the hardware does for us, right? And why. I try to explain you not just, here is the cache, deal with it. I try to explain you why it exists and why it has certain organization without too many details. But as a compiler writer, I have no way to change the hardware itself that's given, but how I can make that hardware more efficient. This is by understanding this key principle, temporal locality and spatial locality. If we realize that the cache operates to benefit from these 2 things, that means we can reason and optimize our code to run more efficiently using these 2 principles, right? So essentially, we always try to improve either temporal or spatial locality of our code, because that would improve ultimately your performance. And what we want to minimize is the number of conflicts or bad replacement decisions. So the question for you, just to check, make sure you don't sleep right now in the lecture. So what are those replacement decisions I'm talking about? Like I never mentioned them, but maybe you at least have a guess. So what I'm talking about, what are those bad replacement decisions that happen? Anyone has any idea what I'm talking about? Okay, anyone want to give it a shot at least?
I can try.
Yeah, go ahead.
So for example, say when you're trying to loop through an array and you have an index I, right?
Yeah.
So first you probably store the array in the cache, but then if you say like you are replacing the whole cache with the nearby data of I, so that you will like evacuate the whole array, which is bad.
Yeah, Frank, you're thinking in the right direction. So just to make it a little bit more precise, so there is not such thing as storing the whole array in the cache. So what happens, your array is a big continuous piece of memory, right? You can allocate it with malloc. It can be like hundreds of megabytes or gigabytes, right? When you start to go through it, right, the cache at the beginning is empty or with some random stuff in it, right? As you start to read the data from the array, I start to bring this data in to the cache. But my cache, as already alluded to you guys, is not infinite in size, right? It has capacity that has a limit. So at some point, I'm gonna take all the space in it. And then when the new data arrives, I will need to take out something to place in new stuff there, right? That decision is called a replacement decision. And if I do that decision in a wrong way, so if I remove something that was about to be accessed, but I just didn't keep it long enough, then what's going to happen is that I'm going to have way more misses because I'm going to kick out something that would be useful, and it means it would make my access latency worse because I'm going to every time I miss into the cache, I have to go to the memory, right? So the best way to think about it, it's a 20x cost mistake. So every time I miss the cache, I have to pay 20x more in latency, right? So essentially, we try to minimize the number of these conflicts when we cannot find something in the cache, right? So, but we can say, well, this is all about hardware, right? The hardware makes these decisions, what to place in, what to take out. How can the poor compiler has to do anything with it, right? It's not involved, right, in the hardware. And the answer is we had some levels in which we can manipulate. Even though we don't have the hardware full control, we are, the software level, define what is an object and when it is accessed. And we defined how the object is allocated in the address space. So it's up to us to decide how to allocate my array or my data structure in the memory. And I can make it one way or another. It depends on how it's allocated. I have different average access latency. So essentially, those time and space are the dimensions on the data structures we can manipulate. So how do we exploit these two levels? So let's talk about the time first. Time, it means we can reorder computation. So what makes it difficult to know when an object is accessed? That's one question we need to answer. How can we predict a better time to access an object? What information is needed? How do we know that this would be safe? So those are the questions we're going to try to answer in this and next lecture when we talk about prefetching. The second dimension is space. Remember, when I write in C, I had a struct with multiple fields, right? It's completely up to me how I define those ones, right? Pointer-based data structure, arrays, all of that are logical objects, but in memory, they had many different ways to be stored. They actually don't, like the usual way we think about it, if I had a struct, right, type that has multiple fields and I had an array, we think everything is continuous, right? But is it always the best way to store it in this way? It might be not. It's maybe natural, just logically to store it, but it might be not the best for performance. So this is why people restructure those data structures sometimes in the compiler, because the programmer like to think about those things as logical abstract structures, right? That somehow map to memory, but we don't want to worry how exactly. But the default allocation might be bad. So this is something we want to deal with. How can we tell what a better layout would be? Again, this is another open problem we need to figure out and how to optimize it afterwards. This is something the compiler can help. Okay. To what extent we can safely alter the layout. Remember, one of the problems with those structs, those are types. So if that type is used in one place and in another place in your code, somewhere very far, you cannot manipulate its storage in one place and not properly change the accesses to this data in the other place. So you need to have a holistic global view on the full program. So you would understand how actually the change in one place affects the change in another place. So you cannot just change things in one place and hopefully save it. It won't affect safety in that place. So what are the types of objects that we're planning to consider? Again, we try to keep it relatively simple here. We're going to look at scalars, we're going to look at structures and pointers, and we're going to look at arrays. So what are the locals? What are the scalars? So there are local variables, right? Like the one variable I here inside the function full, right? Then there are global variables, something that is external to the whole set of functions here, called like x and y. And there are procedures arguments that are temporary things that can be allocated. Remember why we care about those, because they can potentially allocate it differently, stored in a different, address spaces, and such as, there are, we have, heap, we have stack, all of that can be used to store all the scalar variables. So the question is cache performance a concern here? If so, what can be done? So do you think cache can help a lot with like local variables or with procedure arguments? Any ideas here? So what do we normally like? You all hopefully took P58, right? Computation class. You look at assembly code, right? You've seen at least heard about registers, right? So where does those variables usually placed? Hey guys, wake up. That's something you're supposed to know that's not specific to compilers class. So like when I take this C code, I'm gonna generate an assembly language. This is now assignment from the B58 class. So where's the variable I is going to be stored? There's not such things as I in hardware. So what are going to get in their assembly code? If anyone wants to give it a shot?
Like a address to the stack?
It depends. So it can be on the stack, but it can also be just a register, right? So you had a local variable I, most probably going to be used one of the short-lived registers, right? The parameters, those can go on the stack, right? But those variables are not. So is the cache particularly helpful to deal with that or not? What do you think?
I believe no, because they're already very small data structures, so the register could handle those.
Yes, so 99%, Frank, you're correct. But what if you had a machine with just say 16 registers, not something impossible, there are machines like that, and then your function has 20 arguments. So essentially, logically, it's a stack, right? The question is where that stack would be located. The way your programmers think about it as that's a piece of memory being allocated somewhere, right? But ideally, as a, if you run that code, oh my God, you definitely don't want the stack data being in the memory, right? You really want that being on the register. Otherwise, like reading every parameter from the stack would generate another access to memory, right? That would be a nightmare. Every function called would be like super expensive, right? So what usually happens, things logically stored on the stack, but in reality, after optimization, they ended up being in a register, right? But what if you don't have enough registers? So this is where the cache can help, right? So it means even if you miss them, if you had like more stack parameters on the stack that you have registers, remember registers also need here, right? You might not have enough register to keep all those parameters and all the local variables of the function, right? So if that happens, and you don't have enough registers, they will be spilled into the memory. Like that's something you discussed, that's register location. But when you say something is spilled to the memory, it doesn't make that it really go all the way to the memory. It might nicely reside in the cache, right? Because that's what cache is helpful for, right? So the cache can help, but this is more like micro optimizations that's done more or less automatically by the compiler. And more complicated things is structures and pointers. So if you had a struct like that, you see, there is a struct in count, double velocity, right? This is like some general structure. There is a node type, right? It has counter, it has two double parameters, velocity and inertia, and it has a struct node star of neighbors. So it has some neighbors in it, right? So what can we do to improve things within a node and across nodes, right? What limits the compiler ability to optimize here? So let's try to brainstorm a little bit, since otherwise you're very passive. I'm gonna push you in this direction and try to force you to think. So let's first think within a node. If I had a struct like that, how I would want to keep that in the memory or in the cache? Is there anything that the cache can help here, right? Is there anything we can optimize in the compiler to help with that? Let me give you a hint. So imagine that this thing here, right, is stored one by one, right, in the memory. So that's the most trivial one. You give me a struct of node, then you either had a linked list of those or array of those, doesn't matter. You just allocate them in the memory. So the cache, by design, when it's going to read, remember I said that it's never going to bring you only the data you access. So if you're going to access the node velocity, it's not going to just bring you that, 8 bytes, right, or 6 bytes. What it's going to bring is going to bring a 64-byte aligned memory address that you're going to take, pieces of that struct, right? In fact, it's a bit more complicated than that, because the way you're going to write your C code, you're probably going to access node, and then you're going to access the field. But first, we're going to access the node, which is going to be the beginning of the struct, right? And then if that struct is nicely aligned to the 64-byte chunks of the cache, then it's going to bring whatever it can bring. Sometimes maybe a couple of these objects. But what is the problem with that approach? That problem fully anticipates that everything I bring would be useful, right? But dynamically or through some static analysis, I might find that in this particular example of the code, I only access velocity, access the count, but I don't access the neighbors, right? I compute some basic statistic. Maybe I just compute average velocity, right? Something like that. In this function call, all these things don't access. So what happens, they pollute the cache. I'm going to read the memory. It's going to bring all this data to reside in the cache and never touch it. It means that even though I had 16 megabyte cache, for example, and if that's my only one, but very large data structure, then more than half of that memory can be taken with something I actually don't need, right? And never access. So just because I use this basic spatial principle, I might just wasted half of my cache. So if I'm smart enough, I might be able to restructure that node in the compiler to split the structure into two pieces, right? So that, say, for this execution, where I know these two fields are not needed, I remove them and store in some other structure like node 1 or something, and only access this thing. Programmer doesn't want to do this. It can be very error prone, very difficult. So remember, you might also have different versions of the program where sometimes these two are needed and sometimes they're not. But if the compiler can prove those things are not needed in these particular functions, they can optimize the structure and can save you a lot of cache capacity, right? So you can store more objects there. Okay, so this is the possibility of optimizing within a node. How about across the nodes? Across the nodes, we can also learn things about how, for example, these arrays are stored and what their parameters they have. If we know that and we know how things are located in memory, we might actually making sure that we align those pointers in a nice way and access them in a nice way so they would be co-accessed together. So if I know I had to access this guy, this pointer here, I know that if my neighbors are always jumps by, say, 10, when I access this guy, I want to bring these neighbors as well, right, with 10. So I store them in the memory so they will also usefully access almost the same time. It's not always easy, but you can write a dynamic algorithm that can potentially do it. Okay, before going into pointers, because that's the hardest case, let's look at the arrays. Okay, so this is an example array, like AA, NN, and BNN, and this is what I do. I access AIJ, right? So I take, row I, column J, and for B, I take the other way around, right? JI, right? So this is a very typical code we can write, right? Something like, I don't know, transposition and things like that. So this is usually accessed within loops nest, which is make it easier to understand the time of those arrays. The problem is that the way you store this and this might be the same, but the access pattern might be different. So what the compiler wants to do is understand how data is really stored versus how they access, and having a notion of time, knowing when things access one by one, is try to reshape things in the memory so that with respect to time, it will be better. Okay. This is going to be an example I'm going to show now, but since we are out of time right now for the first half, I will stop here and we'll continue after a 10-minute break. Okay. See you in 10 minutes. Okay, everyone, let's come back. Okay, so what we're going to talk now is essentially the way we go over the iteration space and time space. So what does that mean? So when we have a loop like this, we had index variables I and j, right? So what we try to do is try to really understand is how the data is accessed and when we get misses or hits into the cache. So the iteration space, essentially each position represents an iteration. Okay. So how we can think about the visualization in this dimension. So if you look here, I first go over I and then over j, right? So j is the inner index. So essentially, I do first step here for 0, 0, and then I go across this dimension. So the way to think about it is that if nothing has changed, the way I go over the iteration space is this way. This, then here, then this, then here, and so on, right? This is my iteration space. Remember though, the iteration space doesn't equal to the data space. The data might be allocated differently. So this is the dimension with which we can play. So let's look here. So imagine this is the same loop, and we're looking how the accessor to array A behaves versus accessors to array B behave with this iteration space. So let's, so what's important to notice here is that it might actually be different. So let's look at when, to understand that, let's look at the simple examples where we understand how the misses occur. So this is, for example, I plus j index, the top index, and the inner index is 0, and this equals to ij. So what's going to happen when the cache miss is going to happen? Sorry, something happened with my animation here. Very weird. So let me explain what's going to happen here. So what's going to happen is as soon as I have 0, 0 at the beginning, this is zeros. The A0, 0 when accessing these iterations was never in the cache, so that's going to be a miss, right? And this is something that's easy to understand here. Then as I go with the dimension G, right, I'm going to access A10, then A20, then A30. And because the memory in the array is usually allocated, in the, a row by row, right? So because of that, we're actually going to have all these accesses being misses. So there's going to be a miss, another miss, another miss, another miss, because this is all not allocated consecutively. And this dimension is 0, it doesn't change. If this dimension would be something like j, then we won't get a misses here. So our goal when we try to optimize for the cache behavior is trying to avoid the excessive number of misses. So we need to understand when the cache misses occur. For that, we use a thing called locality analysis that tries to understand why and when the misses happen. And then, knowing the locality for our array, we can change the order of iterations or potentially data layout to produce better behavior. And then we want to evaluate the cost of different alternatives and pick the one that works the best for us. Then we try to understand, does the new ordering produce correct results? That's important. And for that, we use a dependence analysis, so we didn't break anything. So let's look at the examples of different loop transformations to do it. Let's look at this example first. I guess here I'll show you why all of that is red. Remember, red means miss and white means hit. So if I had JUI, right, in the loop, as I told you before, because the J is the inner loop dimensions, and in memory, we have two-dimensional array is located this way, A00, A01, A02, A03. This is how it's located in memory row by row. When we access things in a different order, A00, then A1020, every access would be a miss. The problem is that it's not only because it's the misses here, it's because if this dimension n is large enough, by the time I went through the first row here and starts to go for A10, it might be that all the elements here that I use already gone because they get out of cache capacity. And when I go to this line, there is already a miss again. So even though I access A10 here, when I try to access A10 again here, it might have been gone by then. So you might ended up actually every single access here being a miss. So you see, even though things kind of nicely located in the memory, that might be not nice with respect to how we access them. In contrast to that, if we actually go and switch the dimensions of the loop, this is called the loop interchange. And assuming that, every element brings two elements into the memory, what we're gonna get, we're gonna have the alternating hits and misses, right? So by just changing that order, we can already reduce the number of misses by at least half, right? And if you actually had better locality, spatial locality, like for example, if you had, when you access one element, you don't bring just two elements, but you actually bring n elements together, so that instead of 1/2, it can be 1/n, right? So here we assume that when I bring 4 bytes, for example, I bring another 4 bytes together. So you see, just by flipping the dimensions of these loops, I might get much better hit-miss ratio here. This is loop interchange. There are a lot of similar optimizations that can improve performance. The one that you probably heard about called blocking or tiling. This is the one where you essentially, instead of going through the whole array, whole one dimensions, like here, because that's the way we write code, we go through, take I being 0, then go all possibilities for j, and that j might be very long. So by the time I want, like, as if you look here, by the time I came for that element again here, it's already gone, right? So I might have, A00 here, and then I get A10, or here it's interleaved, so 0, 1 essentially. But the thing is, that element that I had in memory will be used here again, right, on the next iteration. But if I go this way and then this way, by the time I get here, it's missed, right? Because it already kicked out of the cache. Oops, let me get back to focus. But there is a way to deal with this problem. This is tiling. So the tiling suggests to, instead of going linearly through the dimensions, is going through our rectangles first. So essentially here, our iteration space is like this, right? Loop interchange can help us a little bit. Like as I showed, we can get every second miss. But instead of doing that, what we can do, we can slice across one of the dimensions. So don't go across J fully, right? Go across J in pieces, right? By using step B. So this essentially slice the dimensionality across one line. So I go this way, but I don't go all the way here. Instead of going to the next iteration of I. Why is it good? Because, for example, these elements have something useful to be reused here. If I go this way, that thing will be kicked out, and this would be a miss. This way, I would have a better reuse, right? Better locality, spatial locality, when my locality is two-dimensional. So this is reduces the number of misses. And you can do the same thing in 2 dimensions. So that's frequently used in different algorithms, such as matrix multiplications. You essentially take the matrix, tile it into subchunks, and instead of multiplying one whole row and another whole row, you do parts of the rows and columns. Okay. Okay, so you essentially try to use every element that is useful to you, like this is essentially matrix multiplications, before moving out to the next piece. So for example, if you had an element that's used multiple times in calculations, make sure you style it such that every use of this variable is done while it's still in the cache until you move into the next tile. Okay. How we can generalize it and make this prediction systematic. So the idea here is to perform locality analysis. So the definition, number one, so reuse means accessing a location that has been accessed in the past. And locality helps us accessing a location that is now found in the cache. The key insight here is that locality only occurs when there is reuse. Like if you reuse something, then there is locality. But reuse that by itself does not necessarily result in locality. So let's say why this happens. So let's look at the data reuse. If the caches were infinitely large, we would be done, but they're not. So essentially, we want to determine in iterations or localized iteration space such that the data accessed by an iteration is expected to be within a cache. So that means that everything I had within this one big iteration would be fully in the cache, so I don't have any misses. So what we do then, we find the intersection between the reuse and that localized iteration space, and that's our locality. So the reuse by itself doesn't guarantee us anything, as I said, right? We need to find the way to exploit it. So let's look at the example how that works in practice. So there are different types of reuses and locality. The first one is called spatial. I'll just use this one tiny example to demonstrate the both. So one is spatial. That's very straightforward, right? When you had ij, right? So essentially, if I had access to 0, 0, then the next access would be to A0, 1. So if I have them at the same time, in the cache, right? And when I bring the first one on the maze, I bring the second block at the same time. That leads to the second hit instead of miss, and that's a spatial locality, right? It's because I had access to 0, 0, I had access to A0, 1 for free, right? Another, locality is temporal. So for example, if we look here, we look at bj plus 1, 0. At the beginning, in the first iteration, when I go through all the j's, right, this is going to be all misses, right? Because it's going to be b1, 0, b2, 0, and so on, right? But on the second iteration, right, because I is small, if things are not kicked out of the cache, because this dimension is small, what's going to happen? This is all going to be hits, because all these elements of B, elements such as B10, B20, all still resides in the cache. So that would be all nicely, hit into the cache. And then that's a group reuse locality. This is a combination of both spatial and temporal. So BJ0 is the example of that, where it's both spatial, right, because you go through this dimension in the spatial direction, and temporal. So that's called the group one, and it's going to be only missed once, right? Okay. Let's move on. So how can we figure out those miss patterns and the locality automatically in a more fundamental mathematical way? So what we want to do is essentially solve the linear equations. So if we had n loop indices that are split into D array, array indices, Y array indexing functions such as this, what we want to find is essentially a representation of these indexes in this form. So essentially what we do, we take the indices matrix and represent this as a matrix H, right? Multiplied by indices. This is essentially our I, J in the direction that the loop are defined. And this is the addition to the indices, right? So if it's not I by I plus 1, we get plus 1 here. So this is, a constant C. Each index is then can be represented using, those matrices. So A would represent it this way, B this way, and Bj plus 1 this way. As you can see here, because I is not used here, you have only, zeros for the I here in both positions, right? Okay, how does that help us? Well, if we want to get the reuse, we need to prove mathematically that the two indices are going to be the same for some values I, where I is a vector, right, at some point in time. So essentially, for that, I just literally need to solve these linear equations. And if you look at it, constants can be removed here. So there's really what I'm looking at is the, the zeros of these matrices, right? So essentially, rather than worrying about individual values of I1 and I2, I can just find the reused direction vector. Direction vector is essentially I1 minus I2, and we need to find the null spaces of the matrix sets. So if we can find the null space of H, we essentially mathematically find all the reuses. And when we know the reuse, we can come up with an iteration space that can help us to, actually benefit from that reuse. So let's look at this example. For example, look at Bj plus 1. Let's look at the reuse between two iterations, I1J1 and I2J2. If I write it this way and then simplify, this is the essentially a system of linear equations I get. Then if, I multiply things here, you're going to see that I1, I2 doesn't depend on anything, right? Because, this thing by this thing and this thing by this thing, this always multiplied by 0. So there's nothing depends on I here, essentially. But what it matters, it's true whenever J1 equals J2, and regardless of the difference between I1 and I2. So essentially, what it tells us is that it goes along the null space of this matrix, which means a span of 1, 0 in the outer loop, right? So it means that as soon as the dimensions of J's are equal, the I can be anything, right? How about, so this is a very simple example. So essentially, reuse doesn't depend on I. And as soon as every iterations where the G is the same is repeated, it's a very easy equation. How about more complicated example, something like this, where you had I plus J. Again, the same thing. This is the representation for I plus J. And then the null space is essentially a span of 1 and minus 1. So essentially, what we have here is we have misses happen only here and at the ends of the iterations. And then there is the reuse on the diagonal. So our vector, right, that we get here is essentially represent 1 minus 1. And that's the direction. This is the null space of A here that is represented by the vector 1 minus 1. And this is the direction in which it goes. So essentially, I only need to touch this element once, and then across these diagonal, it would be the same, because this is here I plus J would be equals to 0. Like would be the same, right? So essentially, you had I1 plus J1 equals I2 plus J2. Okay. Any questions here? Okay, so as you can see, it has a very nice geometrical representation that's easy to argue about. And that's represent the way we want to iterate. So instead of iterate here, we don't want to iterate this way. That's the way we want to iterate, right? If you had this indices. Okay, so how we compute the spatial reuse? Before it was temporal reuse. It's actually quite simple. We just replace last row of H with zeros, creating an HS matrix, and we just find the null space of HS. So that's essentially the same mechanism would help us to find the spatial reuse. And the result would be the vector which we access the same row. Why we zeroed the last dimension? Because this is what the spatial is. The spatial is where everything is variable, is fixed, and the only thing that changes is the last dimensions. This is your spatial reuse, right? So spatial is like a special case, essentially. Okay, so this is an example how we compute the spatial reuse, right? We get the matrix Aij, right, for this. Then we get HS. So remember the matrix H would be 1, 1, but then we make the last row and make it zeros. So this is our matrix HS. And then for that matrix, we found the null space, which has span of 0 and 1. And this is essentially is the same row of INJ along the inner loop, right? That's what it tells us. That's the span which we're looking at. So you can make those things more and more complicated. So for example, if you look here, right, and if you look at the example like this, right? So you might get, so this is in contrast to what you have here when it was IJ. Here's I plus J, right, just one dimension. And if you look for spatial reuse here, this is your matrix, and this is your null space. And essentially the null space here would be a span of 1 minus 1. This is the direction in which it goes, okay? And the null space of HS would be span of 1, 0, and 0, 1. I go in both this and this direction, right? So this is essentially the pattern you're going to get in this case. So if you mathematically find it, it would tell you what is the span that you get. So this is essentially your temporal locality, span of 1 minus 1 going this way. And this is your spatial locality going this way and this way. Okay, then things can be a little bit more complicated with the group reuse. One thing we have there is that we only consider uniformly generated sets. So essentially index expressions differ only by constant terms. So the only thing we need to do is we need to check whether they access the same cache line, right? Say BJ0 and BJ plus 1. If that's the case, then only the leading references suffers all the bulk of cache misses, and the other one, the trailing one, always get into a hit, right? Because what's going to happen, so this guy goes up front, and it kind of, it's like a prefetching. It happens to see all their needed data one iteration in advance, and when I want to access BGA, you already had that access, right? So in that sense, it's relatively simple. So you just need to find when you have a group of those, reuses, you just need to make sure what the leading one it does. Okay. How about the localized iterations, please? So given the finite size case, finite cache capacity, when does reuse results in locality? Remember, right now we defined what the reuse means, right? But at the end of the day, we want that reuse gives us a locality from which we're going to get benefit. So it really depends on, as you can imagine, it depends on the effective cache size. So localized, right, here versus here would depend on that dimension. So you see here, I will iterate from 0 to 8. Here we iterate from 0 to 1 million, right? Depending on, so that's the difference. There is a reuse in both cases, but it's not always result in locality, because this dimension here go beyond the capacity of the loop, right? So in practice, even though there might be some nice group locality here, is because the way we go, by the time we get to the next iteration, everything is gone, right? Because this is where we get out of cache capacity at some point, right? Because it's so long. And because of that, this BG plus 1 here is always going to be result in a miss, right? Here, though, things are different because that dimensionality is small, right? So what's happened after we went through these iterations until 8, when we go to these iterations, we already had it's going to be B20, right, in here. And that was already observed here. So we already had that miss here. So it's going to be reused, okay? So you see the dimensions of the loop and capacity of the cache play a role. Because of that, depending on those loop dimensions, you might either think about it as span 1, 0, and 0, 1 versus a span of 0, 1 here. So essentially the localized here is limited by this dimension. So we can then compute locality formally by looking at the reuse vector space and with the intersections of the localized vector space. Okay, and that gives us locality vector space. For example, here, when we look at bj plus 1, 0, if loops are localized, we're gonna get a span of 1, 0, intersect span of 1, 0 and 0, 1, which lead us to the span of 1, 0. Example, the temporal reuse does result in temporal locality here, right? So temporal reuse help, but the group one doesn't, right? If only the innermost loop is localized, if we only look at this loop alone, then if we don't look across this dimension, then we get span 1 of 0, intersection span 0, 1, we get an empty set here, and that means there's no temporal locality here. So if we're going to look just at this loop alone, there's no temporal locality. If I look at the two nested loop, then there is a temporal locality on top of this, right? Span 1 of 0. So you see, for the same loop, there might be a difference here. Sorry. Okay, this is pretty much everything I have for today. I suggest you that you play with those examples and I showed today on the locality. I try to use the simple examples, but you can obviously try and experiment with more complicated examples and ask questions. Those are essentially the main way the compiler uses to define locality right now on the arrays. So I specifically keep, this lecture focusing on the arrays because that's the simplest data structure we can deal in the compiler. I guess next lecture, we're going to talk about prefetching and we're going to look at dynamically linked data structures such as linked lists or trees. Any questions? Very few people left. Okay. Okay, I assume if you guys had questions afterwards when you guys watch the video, you can ask questions and Piotr and me or Borja will answer those. Okay, if there are no questions, then thank you guys. That's everything I have for today. Okay, thank you guys. Bye.